Professor Dr. N. Ganesh is working as a senior faculty, Department of Computer Science and Engineering, SRM University, City Campus, Vadapalani, Chennai. He has more than 12 years of undergraduate and postgraduate teaching experience, which includes 5 years of research experience. He has trained many corporate batches on technologies such as mainframes, Application Systems 400, SAP, ABAP. He has published 10 articles in both international and national journals. He has presented several papers in both national and international conferences. He has written 4 books which are prescribed in Anna University affiliated colleges, SRM University and Bharat University. His research interests are software engineering, data mining and cloud computing.
Welcome to UGC lecture series in computer science. We are going to see a series of lectures in the subject operating system. This subject is for the students studying in the 5th semester of their BSc degree program. This paper operating system is of paper number 8. In today's lecture, we are going to see few topics from unit 2. In unit 2, there are several topics, out of which we are going to see about semaphores, about the classical problems of synchronization and about monitors. In today's contents, it will be like how the semaphore is being used as a synchronization tool, and we will be seeing what a monitor is, how it is used. Then as a third topic, we will be seeing what are the classical problems that arise from process synchronization, and then we will also see the one of the problem is about the readers and writers problem. So now, what is a semaphore? A semaphore, we have seen about the semaphore in one of our previous lectures. So to have a quick recap, when you cross a railway track, you have a signal board that in our previous days, in our earlier days, we use the signals, hand signals. So the hand signal is, we will be having a signal which will be put on a horizontal and on a vertical basis. If it is on a horizontal basis, which means anyone can use the railway track, that is, you can cross the level crossing using your vehicle, or even the cattle can use the track, or even the human beings can use the railway track. If it is of a vertical means, if the signal has been put on a vertical mean, hand signal, then that railway track has been reserved, which means that railway track, only the train that could pass through a railway track could use that railway track. When the hand signal has been put on a vertical direction like this, then it is not advisable for the human being or for any other commuter to use the railway track. If at all, if they are going to use it, then they will be smashed and dashed by the train engine. So this is called as a semaphore. The way of signaling from horizontal to vertical and from vertical to horizontal is called signaling. Okay, how it is used in the operating system is that as here this semaphore tells us whether a resource is free and whether it could be used by a process that has already made a request for using this resource. So this semaphore gives us an explanation of whether a resource is free or not. It tells us whether a resource is free or not. Now, so this is what we have seen in our earlier lecture. Now here we will see the general synchronization tool for a semaphore. A semaphore, it is usually an integer value. Integer value is nothing but it can use from 0 to n number of values, or it can be a binary semaphore. In the case of a binary semaphore, it can use only values from 0 and 1. Now, if it is of an integer value, then it is called as a counting semaphore. A counting semaphore is one wherein it has an integer value that can range over an unrestricted domain. Unrestricted domain is it can use from 0 to n. That n may vary as 900, 999 or 9999, or it varies. It does not have any limitation, but it should only be an integer value. Such an integer value is called as a counting semaphore. The second tool is a binary semaphore. A binary semaphore is the integer value. It is also an integer. Binary value is also an integer value, but that integer value ranges only from 0 and 1. And if it is of 0 and 1, it is very simple to implement when compared to using an other set of integers, because in the case of other set of integers you are supposed to remember from 0 to n. Let us consider n as a 3-digit number. Maximum 3-digit number that is possible is 999. So instead of using all the 999, all the 3-digit values, if I am going to use either 0 or 1, something like a boolean type, a boolean is true or false. So if it is true, it will be 0. If it is false, it will be 1. So something of that sort. So when we are going to use a binary value, wherein we are going to use only two different values, either 0 or 1. So such a semaphore, we call it as a binary semaphore. So it is here, and this binary semaphore is also called as a mutex locks. So this mutex locks, so here binary semaphore is also called as mutex locks. So this binary semaphore, it can implement a counting semaphore as a binary semaphore. So when you are going to have an integer in terms of zeros and ones, then we call it as mutex locks. So 0 means it is true. It is true in the sense this signal, this track has been reserved for the train to cross across. So at that time, at that juncture, no one else is allowed to cross, or it is allowed to use the railway track, use the resource. So this train and the human beings are said to be the processes. So this process P1, let us consider train has been allocated a process, has been named as process P1. Then this P1 uses this railway track, wherein in the other case, let us consider P2 for human beings. So supposing if the binary value is said to be 1, which means false, which means the resource has been kept free, that is the track has been free, made free, then any human being or any vehicular movement can use this particular railway track. So that is called as 1, and that is what we even say it as the wait and signal. Wait is when it is in a 0 mode, when it is been allocated for the train to cross through, then we call it as a wait mode. Then the other processes has to wait in queue. When the train has crossed in the railway track, then we call it as a signal. Here the railway track is free, the resource is free, so it has been allocated to any other process. That is called as a wait and signal. And if you are going to use it on a integer basis from 0 to n number of values, then we call it as a counting semaphore. And if it is going to use it as a binary basis from either 0 or 1, then we call it as a mutex locks or as a binary semaphore. Then how a semaphore is been implemented? Here, as I said, it works only based on two different functions. One is called wait, other one is called a signal. And this wait and this signal, this wait is again classified into two groups. One is called as a busy waiting, other one is called as non-busy waiting or no busy waiting. In the case of a busy waiting, it enters into a critical section. We have even seen about this critical section in one of our earlier lecture. What is a critical section? A critical section is one, at a single instance of time, only one process could enter into a critical section. And when it is going to enter into a critical section, this process, it has to intimate the other process that it is entering into a critical section. And when it comes out of the critical section, and when it enters into a critical section, it is called as an entry section. Under critical section, it is called as an entry section. And when the process, after entering into a critical section and after making its execution, when it comes out of the critical section, it is called as an exit section. And the remainder things we call it as a remainder section. So when this process goes into a critical section, then a smaller amount of process is going into a critical section, which means that it is of a busy wait. Busy wait is, it is going to, there is the implementation code will be very short when it is in the critical section. Say for example, if a process is going to get executed for 10 milliseconds, then another process, if it is going to get executed only for 2 milliseconds, then the 2 millisecond process will given a priority to enter into a critical section, because it completes its execution, it comes out of the critical section at a faster rate when compared to a process which takes of a period of 10 milliseconds. So this is called a busy waiting, wherein the implementation code is short, because as we know, a process is nothing but a program in execution. And in the case of busy wait, again, the little busy waiting if critical section is rarely occupied. Then the other case is said to be no busy waiting. If it is of no busy waiting, with each semaphore there is an associated waiting queue. Each entry in a waiting queue has two data items. One is value of type integer, other one is a pointer to the next record in the list. So what do you mean by value and what is a pointer? In the case of value, so some integer value is been allocated. In the case of pointer, this process, it should know what is the process that is currently getting executed, because this is said to be my second process, so it will be waiting till the first process completes. So there should be a link from the first process to the second process, or it should know what is the process that is getting executed. I suppose you would have learned in a subject called data structures about a topic called linked list, in which in the linked list that list should contain a link of the next node. So similarly here, this process, it should know the information of the previous process about its execution and its timing. Supposing if there are two processes P1 and P2, and if P1 gets executed, this P2 should know the execution time of P1, so that after that P1 gets executed, after P1 completes its execution, this P2 could enter into this critical section. So that is what is required, and this is been allocated with a value called an integer value. Second one is a pointer. Then it requires, this no busy waiting requires two operations. One is called a block operation, other one is called a wake up operation. A block operation, it is a place where the process invoking the operation on an appropriate waiting queue, where the process has been put on a waiting queue. Whereas in the case of a wake up operation, it removes one of the processes in the waiting queue and place it in the ready queue. If it is a higher priority process, or if the process is going to take only a lesser amount of time to complete its execution, then that process will be taken and it will be allocated and it will be put on a ready queue. A ready queue is a place wherein it will be put on a main memory, so that it gets executed at a faster rate. So these are the two operations that are possible with respect to a no busy waiting. Now the next concept is about the deadlock and starvation. So we have already discussed more about deadlocks and starvation. So we will see how starvation gets implemented. Supposing the process is going to wait for quite a long time, for an indefinite amount of time, then we call it as a starvation. And supposing it means that if it is going to get blocked for a more amount of time, indefinite blocking is called as a starvation. What is a deadlock? A deadlock is two or more number of processes are going to fight for or waiting indefinitely for an event that can be caused by only one of the waiting processes, is called as a deadlock. Even here, consider this to be process P0 and P1, wherein we have both wait and signal. So this is about a deadlock, and starvation is indefinite blocking, is called as a starvation. So we will see about starvation and about its priority inversion after the break. Welcome back after the break. Before the break, we were seeing a topic on deadlock and starvation relating to semaphore. So we have already seen more on deadlocks in one of our earlier lectures. Now we relate this deadlock and starvation to this semaphore. In semaphore, it uses two different functions. One is called as a wait function, other one is a signal function. So here in this program, how the deadlock uses these functions is being seen over here. Here we have two different processes, P0 and P1. One is wait. So here it is waiting and it is signaling. Waiting is it is being put on hold, wherein this is to be a resource S and Q. So it is waiting for resource S and waiting for resource Q. So unless and until other process completes it, it has to wait, and if other process completes it and if the resource is free, then a signal is passed on. So signal of S and signal of Q. Similarly for process P1. And supposing this wait goes on to an indefinite mode, that is, if it is going to wait for an infinite number of timing, then it goes to it gets blocked out. I suppose you would have seen working in the operating systems like Windows 95 or 98 or even 2000. At times, due to some process execution, your system, your desktop will get hanged, and at times what happens is that hang gets released out and it goes to and then it goes on to a normal execution. There are situations where the hang will be prevalent and it will not resume to its original position. Then what do? You either shut down, you either press Alt Control Delete, go to Task Manager, shut down the task, kill the task, kill the process, whatever you have seen, which is running in the background, or even if that is not working, you just switch off the button and then go out, right? So it is called an indefinite blocking. If you get an indefinite wait and if the process is being blocked indefinitely for infinite number of timing, then it is called as a starvation. So in the case of starvation, a process may never be removed from the semaphore queue in which it is suspended, because already the process is suspended for a quite amount of time. If it has been suspended for an indefinite period, then it is called as a starvation. Now, what is a priority inversion? In the case of priority inversion, scheduling problem when lower priority process holds a lock needed by a higher priority process. So in this case, let us consider there are three different processes, out of which process P1 is of lesser priority, or let us consider process P1 has a priority range of 3, process P2 has a priority range of 5, and process P3 has a priority range of 4. So process P1 is 3, process P2 is 5, process P3 is 4. Now, so whichever is said to be the least value is said to have a higher priority. So in this case, P1 gets executed automatically. Now it is with respect to P2 and P3. According to the queue, P2 should get executed, then only P3 can get executed. But in our case, what happens is that P3 has more priority than P2. And this P2 holds the lock, the mutex lock. Mutex lock is a binary semaphore. Holds the mutex lock and it is not allowing it to execute, allowing the other process to execute. So now this has to get inverted in such a way that process P3 executes first and then process P2 executes the next. So such a thing we call it as a priority inversion. A priority inversion is one wherein scheduling problem when lower priority process holds a lock needed by higher priority process, and it is solved via a protocol called as priority inheritance protocol. Now the next topic is on monitors. What is a monitor? A monitor is also similar to semaphore. It is a programming implementation in a program, how it works out. So that is called as a monitor. How the programs are being lined up, how there are n number of loops in a code, how the process takes time for executing each and every loop, each and every iteration. So how it works on a programming construct is called as a a monitor. A monitor, it is a high level abstraction that provides a convenient and effective mechanism for process synchronization. Abstract, it is an abstract data type, internal variables only accessible by code within the procedure, and only one process may be active within the monitor at a time, because we are saying that it is a code construct. For each and every processes a program in execution. So for each and every program, it may have n number of lines of code. In those codes, what happens is that this monitor will be monitoring, will be checking the execution of the code, the process taken, the time taken for executing a set of code. That is called a monitor. So it is a program constraint similar to a semaphore. So this is how it works. It is not a powerful enough to model some synchronization schemes. You have a monitor name, the shared variable declarations, and the procedure names and initialization code. So this is a schema of how a monitor looks like. Then let us now see the structure of a monitor. In the case of structure of monitor, so I said it is about a program construct. It is going to say how the programs are going to work, and it is going to note or monitor or view what is the time taken for executing each and every loops or each and every task that has been put on the process. So here is the structure of a monitor. Here the process, these are the set of processes, and this is said to be a queue. So the queue of entering process, this is said to be our entrance. So what happens is that the data gets separated out, local data, and you have conditions, the condition variables, and you have a set of procedures. So when a local data has been set out, then it monitors. When the code enters inside, this monitor checks whether it has sufficient set of data. When the condition variables have been put, if a greater than b, then do this, if that is the code snippet, right? What is a code snippet? Part of code. If a greater than b, then printf, then print a is said to be bigger than b, else print b is bigger. If this is my code, wherein a and b are said to be my variables, and if a greater than b, then print else. So these are said to be the condition. We are giving a condition where if a is greater than b, then do something. If it is not, then do something. So we instruct the computer to work in such a way that if it is true, work in a different way. If it is false, work in a different way. So this has to be monitored. So this is being done by a monitor. Now we have a condition variable. This condition variable, if a is greater than b, for one instance, say for example this a, if in this condition, if a greater than b is being put inside a single loop. So when it is in a single loop, at one point of time a may be greater and it will be printing a is greater than b, and at the second point of time there is a possibility a may be lesser, so it will go to the else part and it will print as b is greater than a. So in that case what happens now? So all these conditions have to be checked. So when b becomes greater, then the variable a waits, and when a is greater, b waits. So this has to be at that juncture, this has to be put on waiting queue. So this is how it represents. So in the waiting queue, the conditions have been loaded in the waiting queue. Then the procedure executes. Inside a procedure there may be n number of conditions. So all those conditions will be put on a condition waiting queue. There may be priority for executing the processes. So all these things will be put on a urgent queue, and then again it goes on to an initializing code. So till the completion, till the working gets completed, from entry to exit is the job of a monitor. So now let us see the common problems in semaphore. So what are the possible problems in semaphore? I said you have two different semaphore uses two different functions. One is wait, other one is signal. Supposing we are not going to use the wait signal or the wait function or the signal function in a proper way, then it enters into a problematic situation. Then the next thing is omitting of wait or signal or both. Incorrect usage of these things will cause problems in working with semaphores. The next problem of semaphore is about deadlock and starvation. In starvation, if it is of an indefinite blocking, then it goes to starvation. If it is of if two or more processes going to wait for a single resource, then it enters into a deadlock state. Even that is also a problem with a semaphore. Now let us see certain classical problems of this process synchronization. What are the problems? Like we have a problem called readers writers problem. In one of our earlier lecture, we have seen a problem called producer consumer problem. Even that is also a classical problem. So now we will see one other problem called readers writers problem, which is a problem of synchronization, process synchronization. So what is a reader writer problem? From the name, what can you infer? From the name, it means that if a file has been read by this process, it can read at a single instance of time, and you can write the contents of the file at a single instance of time. That is, a file can be read and a file can be written. Contents in the file can be written. And one more thing is, n number of readers can read at the same instance of time, because it is about the shared memory. The data has been shared, the memory has been shared, so you are going to read. When a file has been, when the document has been put, when a file has been put, it is going to read. So n number of users can read, but an updation, when it comes to updation, at single instance of time, only one particular person could update that file, and then the other persons can update. One by one only can update the file. So readers, n number of readers can read, and writer, only one person can write a file. So we will see what are the problems in reader and writer problem. A data set is shared among a number of concurrent processes. Readers only read the data, writers can write the data. When they are going to write the data, they are supposed to read the data even. So they have the option of both reading and writing. The problem is, it allows multiple readers to read at the same instance of time. Only one writer can access the shared data at the same time, because only he has to read the data, and then based on his reading, he is supposed to modify, he is supposed to write the contents. These are the shared data will be like data set, and about a semaphore mutex, and about an integer read count. Then these are the variations available. One is about a first variation and a second variation. In the first variation, no reader is kept waiting unless the writer has permission to use a shared object. In the second variation, once the writer is ready, it performs write as soon as possible. But both variation may have starvation, leading to even more variations. So starvation is indefinite blocking. So this problem is solved on some system by kernels providing reader writer locks. We will now summarize whatever we have seen in today's lecture. So we have seen topics on, we have learnt about semaphore as a synchronization tool. We have as well seen about the monitors and how the monitors are being used. We have discussed the problems of the classical problems of process synchronization. We have learnt about the readers writers problem. Now let us see the possible questions that could arise from today's lecture. Question number 1 is, mention the different synchronization tool used by semaphores. Question number 2, what is starvation? Question number 3, what is a mutex lock? Question number 4, what is a monitor? Question number 5, what are the problems of process synchronization? Question number 6, what is a reader writer problem? So with this, we come to the end of today's lecture. We will see more topics on operating system in our forthcoming lectures.